folks, Ms. Gosling here. In this video, we are going to go over the HL extension for wave behavior. Specifically, this video is going to look at the Doppler effect. So by the end of the video, you'll be able to solve problems involving the Doppler effect and describe some of the uses of the Doppler effect outside of the physics classroom. So let's go ahead and get started. So we most commonly experience the Doppler effect with sound waves. If you've ever been standing somewhere and you hear, say, an ambulance or a fire truck go by, what you'll often hear is that the sound of the pitch of the sound of the siren is going to change as the ambulance approaches you. Specifically, the frequency of sound is going to be higher as the ambulance comes towards you, and then once it passes you, you'll hear that the sound gets lower. And you can see in the diagram why that happens. So as my ambulance is approaching me, you can see my wavefronts are getting squished together. And that's because as my ambulance approaches me, each wavefront is going to be emitted closer to the wavefront that was previously emitted, since we have to add in the speed of that car. Similarly, away from me, each additional wavefront, going away from you, so going away from, say, person A, each additional wavefront is actually going to be further away from where it would be if we had a stationary source. So that observed frequency is going to be lower, that sound pitch is going to be lower. So when we have a source that is moving, so we have our ambulance going at some speed u, which I'm going to call us since it's the source of our sound. And it's emitting sound at a frequency of f and a speed of v. What we'll find actually is that the observer is going to hear a different frequency, which I'm going to call f prime. And f prime is going to be equal to the emitted frequency f times the speed of, in this case, sound, divided by the speed of sound plus or minus the speed of my source. Now, I say plus or minus because, of course, when my source is going towards you, the frequency is going to increase, and when my source is going away from me, my frequency will decrease. So that means if my source is coming towards me, I am going to go ahead and subtract. So u is going to be negative when when source is coming towards me. So I'm going to call this person B and person A. So for person B, we're going to see a negative US, and our frequency is going to increase. For person A, we're going to have a positive US because we're going away from you. And so that is going to decrease our frequency since our denominator is going to increase. So again, we're going to add the speed of our moving source to the speed of sound when our sound is moving away from us, and we'll subtract it if it's moving towards us. Now we can kind of think of this by looking at the number line or by looking at just that picture of what our compressed wavefronts are going to look like. So now let's go ahead and talk about another situation. So what if my ambulance is not moving, but I am? So maybe I'm moving towards it, situation A, or away from it, situation B. So similarly, I'm going to be picking up those sound waves either closer together or farther apart than I would expect to. So again, I'm going to have to think about how the speed of my observer is going to affect my observed frequency. So when we are moving away from when we're moving towards our source, the observed frequency is going to be equal to the speed of sound, or light, or whatever the wave is, plus the speed of the observer, divided by that total speed of my emitted wave. If I'm moving away from my source, I'm going to go ahead and subtract that velocity, subtract my speed. So again, this time, positive is if I am going towards my source, and negative is if I am moving away from my source. And you'll notice that is the exact opposite of what we observed last time. We had the negative when my source was moving towards me and the positive u when it was moving away from me. So just important to remember, we flip which is negative and which is positive based off of whether the source or the observer is moving. And you're going to just have to learn which positive, which negative goes with which. Or you can remember this picture, think about what we expect to see with our wave fronts and therefore with our frequencies. So that's kind of your two options there. So the last thing I want to talk about is what happens if instead of emitting sound, we're emitting light. So instead of this being being an ambulance, we're going to make it the Andromeda Galaxy, which is going to be emitting light. Now, one of the things that, this is going to be following the same rules that it would follow if we were looking at a sound wave. But of course, this being light, the emitted radiation is of course going to travel at the speed of light. So what we will write then is that the speed that we on Earth observe, the frequency of light that we observe on Earth is going to equal the frequency of that's being emitted by the Andromeda Galaxy times the speed of light divided by the speed of light plus the speed of my Andromeda Galaxy. Or, simplifying a little bit, it's going to equal F times 1 over 1 plus the speed of the Andromeda Galaxy divided by the speed of light. Now, why did I go into light specifically? What's so special about this? Well, one thing that's really interesting actually is that one of the things we know about our universe is that it's expanding. And one reason that we know it's expanding is something called redshift. So objects that are moving away from us are going to have a lower frequency, are going to appear redder than we expect it to, or than we expect them to based off of their makeup. So we can figure out what color we expect a galaxy, or honestly more commonly something like a star, to look like, what we expect it to emit, and we can figure that out through a bunch of different things. But what we'll see is that if something is moving away from us, it is going to have something that we call a redshift. So every frequency is going to be a little bit lower than we expected to see. Every wavelength will be a little higher. And it's called redshift because, of course, we're going towards the red end of the electromagnetic spectrum. And what's really cool about this is that's actually helped us confirm the fact that our galaxy, or our universe is expanding. So that's one of the cool practical uses of the Doppler effect. So let's talk takeaways. And there's actually only one, so really I probably should have just written takeaway. And that is the relative velocity between the source and the observer affects the wave frequency perceived by the observer. And we call this, of course, the Doppler effect. So now it's your turn to try solving some Doppler effect problems. Best of luck and happy solving.